This lesson will be the second part about limits involving infinity. So last time we discussed cases where x was approaching a constant value, and the limit itself was infinity, or negative infinity. In these cases, we'll be discussing what happens as x actually approaches infinity, or negative infinity. In these cases, a few things can occur. First, the limit can be infinity. The limit can be negative infinity. The limit can not exist. Or the limit can approach a constant value. Many functions will approach an infinity as the x approaches an infinity. The simplest example is just y equals x. You can analyze this graphically. It's just a straight line. And you can see that as x increases, y is also increasing. So as x gets larger and larger and closer to infinity, then y will also get larger and larger and closer to infinity. So here we would just have something like limit as x approaches infinity of our function, and that would equal infinity. Likewise, we can say that limit as x approaches negative infinity of our function, that equals negative infinity. If instead, for example, our function was y equals the absolute value of x, where we would have a graph that looked like this, then our limit as x approached negative infinity would not be negative infinity, but it would also be infinity. In other cases, the function will approach a constant at infinity. So examples of this can be something like a rational function, y equals 1 over x, where our function approaches 0. You can tell by the graph. Or something like y equals e to the power of negative x. So our graph would look something like this. And then you could say that as x approaches infinity, y approaches 0. But note that as x approaches negative infinity, y approaches infinity. Let's examine the case with rational functions even further. We'll have a rational function f of x, and that can be written as g of x over h of x, where g is a polynomial of degree m, and h is a polynomial of degree n. Now, there are three things that can happen. First, we can have that m is less than n. In that case, we have that x equals 0 is a horizontal asymptote. And f of x approaches 0 as x approaches infinity and negative infinity. The reason this happens is because as x increases to very, very large values, the polynomials g and h are dominated by the term with the highest order. This means that when we're trying to find the limiting values, we can only consider these terms. So if we had something like x squared plus a bunch of other terms of lower degree over x cubed plus a bunch of other terms of lower degree, then eventually when you get to have very large x, the only terms that matter are these first two. And we can intuitively reason that x cubed is going to be much, much larger than x squared, so much larger that our value is quite close to 0. The second case is m equals n. Now we'll have to look at the polynomials g of x and h of x a bit closer. We'll say that g of x has a term of highest order, a times x to the m, and then h of x has a term of highest order, b times x to the n. So that means that our function looks something like ax to the m plus a bunch of other terms over bx to the n plus a bunch of other terms. When this happens, then we have a horizontal asymptote at x equals a over b. The reasoning behind this is similar for the first case. As x becomes very large, the dominant terms are the ones with the greatest degree. And so our function would be very similar to ax to the m over bx to the n for large x. And since m equals n, we can cancel out these two terms, and what we're left with is a over b. The last case is where m is greater than n. In these cases, we have a polynomial as our asymptote. So for example, if m is greater than n by 1, or m equals n plus 1, then we have a slant asymptote, or an oblique asymptote, which is just the graph of a line. If m is greater than n by 2, then we would have m equals n plus 2, and in this case, we would have a quadratic asymptote. Similarly, if n is greater than n by 3, then you would end up with a cubic asymptote, and so on.